So let's begin actually implementing this code. So let's go into LabVIEW. We're going to put this right in our autonomous mode. So we open our autonomous mode program up. Go to the block diagram. Recall that our autonomous code goes here and start programming. So the fundamental structures we need whenever we have a state machine are a while loop with a shift register and a case structure. So let's go ahead and create that. From my NXT programming palette, structures, while loop, place it down. Create our shift register by right-clicking on the edge, add shift register. And we're going to define the type and initialize the value at the same time by wiring in a string constant here. So by going to NXT programming, string constant, this is going to allow us to initialize our state, which we're going to call idle. As soon as we wire that up to the left side of the shift register, the data type turns to string and both left and right side terminals turn pink. Next we've got our case structure, which we're going to place down inside the while loop. Give ourselves lots of room for stuff both before and after. Maybe expand things out a little bit, but do our best to stay on one screen here. And wire up the state that's coming from our shift register into the case selector. Just to keep things nice and tidy, just move it down so everything's lined up. So the first thing we're going to program is our idle case. So we go ahead and call this guy idle by changing the name, just like we saw in last week's webinar. And the first thing that we're going to need to do is read our ultrasonic detector. So we know how to do this. It's in our NXT.io sensor palette. Place it down, choose the right sensor, read ultrasonic, choose the right port, and for this robot configuration that's port 2. Do a comparison, as we've seen several times already throughout this webinar series. We're going to look at that value and see if something's close by saying if something is less than 10, then we call that something detected. Okay, so this is the first time we're going to actually see the use of a nested case structure. So we've got an outer case structure. This is our state for the idle. But if we return just quickly to our state diagram, we see from our idle state, we're not going to do anything until our ultrasonic detector sees an object. So we have a case structure then inside our existing case structure. Place it down, wire the selector up to the output of our comparison function. And if the state is true, if the object detected is true, then we're going to transition our state to a new state called start motor forward. And then because that's the state we want to implement the next time through the loop, that goes into the right side of the shift register. So this isn't that different from what we saw last week. What we also saw last week is that when we have an idle case, if nothing is detected and we don't want to change states, we can just pass the value from our shift register right on through. And so if we're in the idle state and this result is false, we're going to stay in the idle state. And that's exactly what we want to have happen. So the next state we're going to implement is the start motor forward. We're going to take advantage of the false case that's been here by default. Call it start motor forward. It's a great time to take a step back, make sure we didn't spell anything wrong. Start motor forward, start motor forward. Perfect. The most likely cause of errors in this kind of programming are actually typos, so we've got to be careful. And in start motor forward, what we're going to do here is basically, well, start our DC motors. So we're going to go to our Tetrix palette, put down a DC move motors. As we've done a whole bunch of times, create a constant for our motor. Also, as we've done a whole bunch of times, we're going to pull that outside the loop so that we can call it from many places. We've got our left wheel, we expand, we've got our right wheel. Move this guy over a bit and then wire him back in. And if we're going to move forward, all we've got to do is define a speed. In this case, it doesn't matter too much. We'll just choose 50 for both of them, and that'll make sure that we go in the straightforward direction. And we're just going to realign things a little bit just to keep things clean, because I know I want to line up this NXT terminal with the output from that one. So we're almost done with the start motor forward state, and let's just step back into the state diagram to see what it's supposed to do. Well, start motor forward starts the motor, which we've done, and then it goes into the moving forward state. So let's do that. We've got to right click here, create a constant, and say moving forward. Now we've programmed up already our idle and our start motor forward case. So let's take a quick look at the moving forward state. So this guy's a little bit different. Here we're actually going to be checking for two different sensors. One is the touch sensor and the other is the ultrasonic sensor. So let's keep that in mind as we program that code. Now that we have used up our two default cases here, we need to create a new one. So we can right click, say add case after, give it the right name, moving forward. And now what we've got to do is code up our ultrasonic sensor, but one thing we need to do is we also need to read our touch sensor. So we didn't need it in this state or this state, but now that we do, I want to observe something else. That touch sensor is not just read in the moving forward state, it's also read in the moving backward state. So thinking ahead to reusing code and making things as simple and easy as possible, we can actually put our touch sensor read out here rather than inside the state. Because if we had it inside here, we'd have to duplicate it. So let's get rid of this NXT terminal wire for now. Move this comparison function around a little bit to give us some space. Go back to our sensor palette and read the touch sensor pressed. That's great. Line it up so that our terminals are all there wired up. And pick our port, which for this robot configuration should be port 4. And now we've got a touch sensor being read. Let's clean things up a little bit so we can see all of our wires. Maybe just quickly step back into the start motor forward, make sure everything's still lined up okay. Yeah, looks pretty good. So we can tweak our position a little bit. The way you lay out your functions and your wires, it's really more of a stylistic thing than anything else. But as someone who's been programming LabVIEW for an awfully long time, keeping things lined up as you go will always make your day shorter at the very end. So we're going to go back to our moving forward case. Now we've got a touch sensor reading and an ultrasonic sensor reading here. And now we've got to implement this logic. So we've got either the transition to the stop state or the transition to the start motor backward state, depending on the value of these guys. And here's where we're going to use another nested case structure. So in our outer case structure, we're going to first check the touch sensor. And if that touch sensor is read, we're going to transition into the stop motor state. So I'm going to take a nice little shortcut, control drag this string constant, put it in here called stop motor as the name of the new state, and wire it on through. So now if we don't have our touch sensor pressed, we're going to be in the false case of the outer case structure, and now we need a nested case structure to deal with the ultrasonic detector. And in this case, if an object is detected, then we're going to transition into start motor backward. So again, we bring this constant in here. Start motor backward and wire it up through. So this is where these nested case structures can get a little bit complicated, but as long as you follow the logic through carefully, it shouldn't be a problem. The last thing we need to wire up is the false case. So this is where no touch sensor is pressed and no object is detected. Well, where does the state do then? Well, this is where this approach to the state machine is a little bit different than last week's. The moving forward state will stay exactly where it is. So again, just like in the idle state, wire this guy on through, and now we've completely coded up our moving forward state. So now in a few minutes, we've basically programmed more than half of our code. And here's the nice thing about reusing code and similarities and the way we've structured this particular code, that the moving backward and the start motor backward are actually very, very similar cases to what we've already programmed. So let's look at the start motor backward state. So start motor backward, the idea here, naturally, is to start the motor moving backward. But let's do a little trick here. Let's start with the start motor forward case and just duplicate it. By right-clicking on the top, we say duplicate case. We give it a name, start motor backward. Clearly, since we're going to go backwards, we want to change our speed to be -50. And instead of transitioning to moving forward, we're going to transition to moving backward. So we change our code here to be moving backward. And now we're nearly done this whole code. So the moving backward state, well, let's take a look at it. The moving backward also reads an ultrasonic detector and reads a touch sensor. So the moving backward state is almost the same as the moving forward state. So let's do that same trick again. We go to moving forward, we duplicate it, we call it moving backward, and we just check our logic a little bit. So if a touch sensor is pressed, we go to stop motor, perfect. If a touch sensor is not pressed but an object is detected, do we go to start motor backward? No. We're going to go to start motor forward. And if nothing happens, then we just wire on through. So we've managed to implement moving backward and start motor backward by basically duplicating two cases and changing one minus sign and one string constant. So the last thing we need to do is code up this guy, stop motor. So this guy is similar to the other ones, but let's create a new case for him because it's not exactly the same like we just saw. So we're going to right click, add case after, and call it stop motor. And here what we're going to do is we're going to just put a Tetrix stop DC motors command down, wire up our motors constant, wire up our NXT terminal, and we're pretty good. The last thing we need to do here is define where he goes. So stop motor, if we look carefully at our state diagram, goes back to the idle state. So let's put that in, right click, create constant, put in idle, and we're almost completely done here. There's a couple things that we need to take special attention to look into. So the first is this stop. So our while loop in this state diagram really never finishes executing. Even if you push the touch sensor to stop the robot, it goes back to the idle case. So we don't really need to stop this. So we're going to create a constant here whose value is false, which will make sure the loop continues forever. The next thing we need to do is we're going to see that because if we have a broken arrow, the next thing is we're going to see we have a broken arrow here because we've not defined a default case in our case structure. This is a topic that we discussed last week as well. It's just important to make sure you pick one of your states. In this case, we'll pick the idle state to be the default one. So all we have to do is right click and say, make this the default case. And what that will do is that'll make sure that if we have a typo or for any other reason we go to a state that hasn't been defined, we're going to make sure that we go to the idle state. And the last piece that we need to implement is we're going to create a short delay in our loop. And there's a couple of reasons for this. Let's go ahead and place it though. We're going to go to the NXT.io palette, put down a wait for time. I think we can do a millisecond wait. How about a delay of 50 milliseconds? Right click, create constant 50. We've seen these wait functions before. It's important to wire them up to an NXT terminal to make sure that we have a controlled sequencing. So let's do that. We'll take our NXT terminal from our idle case left side, wire it on through, just reposition things a little bit, make sure they're nice and clean. And now we've got an open tunnel here because we've got to wire through to this right side every single one of our states. So that just takes a minute. So we cycle through all of our cases, wiring up our NXT terminals. And our stop motor. Now we're done. We see that our code is good to go. It's no longer broken. So this delay is an interesting thing. There's a couple of reasons to put it there, and it's worth discussing. One is the concept of a debounce. That the ultrasonic detector is being used, if we look at our state diagram, to flip between moving forward and moving backwards. If we had not put a delay there, we'd very commonly observe the robot stuttering back and forth really quickly. And the reason for that is we haven't provided enough of a delay for it to wait before that sensor reading will go away. In other words, it'll cycle immediately from moving forward to moving backwards to moving forward to moving backwards. By having a delay there, you can control the responsivity. The other thing is overall our loops respond better when there's a short delay. That makes sure that everything has time to function. And the third reason is, and this is a subtlety that I don't want to cause too much complexity for people, but there is a watchdog timer that's behind the scenes in the running in LabVIEW here to make sure that our Tetrix robots perform properly if the code were to fail. And by putting a delay in there, that makes sure that that watchdog timer gets hit. So for those of you who have been familiar with programming in LabVIEW for Tetrix in previous years, there's a watchdog timer function. NI has simplified the usage of the watchdog by embedding it directly within the wait. So by using the wait, we can make sure that that watchdog timer is hit if we're going to be sitting in either our moving forward or our moving backward states where nothing's happening. So I strongly suggest you give this code a try. You're going to find quite positively, I hope, that the system is really responsive as opposed to the state diagram and the state machine that we implemented last week, which always caused at least a 1-second delay before anything would happen. This system is responding within 50 milliseconds to your ultrasonic detector and your touch sensor. And the greatest thing about this approach in general, and using it in LabVIEW in particular, is that this state diagram is now really extensible. Not only was it easy to create, but we could add a new state really easily. All we have to do is change which state gets transitioned to. So we could have another state between moving forward and moving backwards, which was a turn. We could draw that here as a new circle, and all we'd have to do is duplicate these guys and change the way the transitions work. So just want to quickly summarize this week's webinar. We investigated a bigger state machine of the state diagram we see here. We learned how to create nested case structures to implement more complicated logic. We saw how the benefits of reusable code allow us to reuse states and to duplicate them really easily. And we learned the importance of proper state machine architecture, including delays and waits and transition statements, so that we could implement arbitrarily complex state machines. So please stand by till next week's webinar, where we're going to talk about some of the more advanced concepts which are relevant to FTC programmers. And thank you very much for joining us.